So now the equilibrium expression is actually the equation that we will use to express the Kc value, or what we call the equilibrium concentration value. In here you have this reaction, you have hydrogen reacting with iodine to give hydrogen iodide. So your equilibrium expression would be the equation that represents this value of the Kc. So if I looked at the Kc value is actually equal the concentration of my product to the power of the number of moles of my product divided by the concentration of my reactants to the power also of the number of moles for each one of them. But because it's only one, we don't write it. Now, if I looked at the concentration in here of the hydrogen and iodine, if I use the different concentration of hydrogen gas with iodine gas, what I will get is actually a different value of hydrogen iodide. But because equilibrium concentration is a ratio, it's just a ratio between the product and the reactants, this is why you could see here the value is almost the same. So I'm just between the value 161, 159, so all of them is around the range of 161. So the equilibrium expression is this equation that we represent the equilibrium concentration with, and this is my equilibrium concentration, and the equilibrium concentration should have a constant value or a ratio between the concentration of my products divided by the concentration of my reactants. So now if you try to find the equilibrium expression of this reaction, you will find it to be the concentration of my product divided by the concentration of my reactants, and each one of them have to be to the power of to the number of moles of my concentration. So in here I have C to the power B multiplied by D to the power Q, and divided by in that case A to the power M and B to the power N. Now let's look at this exercise. Write an expression for Kc, the equilibrium concentration of this reaction. In here I have nitrogen reacting with hydrogen to give me ammonia. So in order to get the expression, I need my equilibrium concentration. In that case would be equal to the product, which is ammonia, to the power of the number of mole. In here I have 2 moles, divided by my reactants, and in here I have nitrogen gas to the power 1, multiplied by, we usually don't write here 1, and here I have hydrogen, so I will write here hydrogen, and I have here 3 moles, so I multiply by 3. This is my equilibrium expression, and this is my equilibrium concentration. Now what if one of my products or my reactants is a solid? In that case we will ignore the concentration of the solid, because usually we don't you don't have a concentration for a solid. There is no liquid to calculate the concentration for, so you will ignore the part which consists of solids. In here I have silver ions reacting with the iron ions to give me silver solid and iron ion. My equilibrium expression in that case would be the equilibrium constant would be equal to the product, which is the iron ions, divided by the reactants, which is the iron ion and the silver ion. You have to remember we ignored the silver solid because we don't consider the solid concentration. Now, if we look at the equilibrium constant, it has no unit. So if I write down the equilibrium expression for this reaction, I have Kc, which is my equilibrium concentration, is equal to hydrogen iodide concentration to the power 2, divided by the concentration of hydrogen and iodine. Now, if I write down the units, you could see that the concentration unit is mole per cubic decimeter. So it is mole decimeter minus 3. And then here I have 2, because I have 2, the concentration here is multiplied by the number of moles, which is 2. And down here I have also the 2 units of concentration, mole decimeter minus 3, and multiplied by mole decimeter minus 3. So in here you could see they cancel each other, and for that my equilibrium constant has no unit. Now let's look at this exercise. In here I have ethanoic acid reacting with ethanol to give me ethyl ethanoate and water. If I used 500 cubic centimeter of the reaction mixture at equilibrium, which contained 0.235 moles of ethanoic acid. So in here I have the number of moles of my ethanoic acid is equal to 0.235 moles. And for ethanol the number of moles is 0.0350 moles together with so my reaction container, because this is an equilibrium, I had also 0.182 moles of ethyl ethanoate, and I had also 0.182 moles of water. So now what I need to do is actually calculate the equilibrium constant, and you have to remember here I have 500 cubic centimeter of my reaction mixture. So each one of them, and here I have moles, so I have to divide each one of them by my concentration. So in that case I will divide here by 500. And I need to convert my cubic centimeter to decimeter, so I'm gonna multiply here by 1000. I will do the same with each one of them. So in here I will divide also by 500 and multiply by 1000. And in here I will do the same, here multiplied by 1000, and I will divide here by the 500. And in here I will multiply by the 1000 and divide here by 500. You have to remember that 500 is the 500 of my reaction mixture, and for the 1000 is to convert the cubic centimeter to the cubic decimeter. Now if you calculate this one, you will find out that in that one, if you calculate the first one, in that case it will be 0.470 moles per cubic decimeter. Now for this one it is equal to 0.070 moles per cubic decimeter, and in here I have also 0.364 moles per cubic decimeter, and last one is will be the same because they have the same value, so 0.64 moles per cubic decimeter. So my concentration equilibrium would be equal to, I will divide my product divided by my reactants, but here the number of moles is 1 for each one of them, so I have the power of my reaction is to the power 1. So in here I will multiply the 0.364 multiplied by the concentration of my water, which is also equal 0.364 divided by the concentration of my ethanoic acid, which is equal to 0.470 multiplied by the concentration of my ethanol, which is 0.070. If you calculate this one, you will find out that in here I have 0.03. And you have to remember the unit in here, you don't have any unit here because the unit of this concentration would be cancelled with this one, and this one will be cancelled with that one, so I have here no unit. Now let's look at this exercise. In here I have propanone that's reacting with hydrogen cyanide to give me this product. If I have the initial concentration of my propanone is equal to 0.0500 moles per cubic decimeter. In here I have hydrogen cyanide has the same concentration, 0.0500 moles per cubic decimeter. Now if I lift my reaction to reach equilibrium at room temperature, at equilibrium the concentration of my product is equal to 233 moles per cubic decimeter. So my final concentration of my product is equal to 0.033 233 moles per cubic decimeter. So now I need to know the concentration of my the concentration of my propanone, the final concentration, and the final concentration of the hydrogen cyanide. So we could assume that it is actually equal 0.0500 minus the concentration of my product, because they will all exist at the same container. So the concentration in that case will be would be the concentration of my product and my reactants. So I started with 0.05 propanone. This means if I end here by 0.233 moles cubic decimeter of my product, this means I can just minus that from my value. So in here I have 0.0233. This is the final concentration of the propanone, and for hydrogen cyanide it will be the same 0.0500 minus 0.0233. So if I need to find out the equilibrium concentration, in that case it will be equal to my product, the concentration of my product, moles per cubic decimeter, and in here I will just calculate this one, 0.0500 minus 0.0233 multiplied by 0.0500 minus 0.0233. So I can find out the equilibrium concentration in that case, and the value in that case would be equal to 32.7. Now, if I looked at the equilibrium concentration relation and the concentration change, you will find out that if you change the concentration of your reaction, what will happen is actually a change in the products as well, and your equilibrium concentration should not be affected. So example for that, like we seen in the first example, in here, whenever I changed the concentration of my reactants, what happened is actually a change on the concentration of my products. This is why in here you could see that the ratio between the reactants, my equilibrium concentration is actually a ratio between the reactants and the product. This is why it remained the same regardless the change that happened to one of the concentration of my reaction. Now, what about the equilibrium concentration and the pressure or temperature? So like we said before, what I have is actually the equilibrium concentration is a ratio between the concentration of my product divided by the concentration of my reactants. This is why the ratio never changes, and that change would only affect or shift the equilibrium towards opposing this change. By that we came to the end of our video. In next video we will talk about equilibrium gas reactions. We will also talk about the equilibrium constant for reactions that include gases. Until next video, thank you and goodbye.